And a couple more examples. Let's do exercise 3.3.78, which states that the power rule holds for negative integers. Now, here's where we stand in terms of the power rule. We've established the power rule for positive integers. We proved it. It was that thing where we had z to the n minus x to the n, and we went through and factored it a funny way, and a bunch of things simplified. We use the alternative definition of derivative in that case. But that's the only case in which we've proved the power rule. Now, we've claimed that you differentiate x to some power by bringing that exponent down and subtracting 1 from the exponent. We've claimed that works no matter what the exponent is, provided the function and the derivative are in fact defined. But we've only established that, we've only proved it for positive integer powers. We haven't proved it even for negative integer powers, but we're about to. Later on, we'll prove it in general once we've dealt with exponential functions. So what we're showing specifically here, and that's the reason we're showing it here, we haven't done this yet in terms of establishing it. We've only claimed some things. Suppose m is a positive integer, and we differentiate x to the negative m power. Okay, well, if m is a positive integer, then negative m is a negative integer. We're dealing with a negative integer power of x. X to the negative 1, x to the negative 2, and so forth. And the claim is you differentiate that by bringing this exponent down and subtracting 1 from the exponent. No great surprise. The surprise is we haven't shown this yet. We'll do this using the quotient rule. Negative exponents are related to quotients, and that's why we'll do that now. And we already know the power rule for positive integers. And what we'll introduce here actually involves x to a positive integer power. So we'll write x to the negative m as a quotient. X to the negative m is 1 over x to the m. That's what negative exponents mean. Now we got a quotient. Well, I know how to differentiate quotients. Provided I know how to differentiate the numerator, no problem. And the denominator, no problem. I know how to differentiate x to the m when m is a positive integer. We'll use the power rule for positive integers that we proved earlier. Okay. So to differentiate x to the negative m, we'll simply write it as a quotient and apply the quotient rule. That would be the derivative of the numerator times the denominator minus numerator times the derivative of the denominator over the denominator squared. So the quotient rule tells us the form of that derivative. I haven't differentiated these constituent parts just yet. So next page, rewrite what we had. Derivative of 1, let's do the differentiation now. Derivative of 1 is 0. Derivative of x to the m is mx to the m minus 1. We know that. We do know that. That's the power rule for positive integers. There in 3.3.b, I guess, for specific reference. Okay, let's clean that up a little bit. The 0 times, that disappears. Drop the 1, and we've got negative m x to the m minus 1 divided by x to the 2m. When dividing, subtract exponents. So we'll bring a negative 2 up to the top in that exponent. And m minus 1 minus 2m, m minus 2m is negative m. And sure enough, we're left with negative m x to the negative m minus 1. That was the claim, and there's the proof. And so the power rule holds for negative integers as well, and we have proven it. Still left to be done, even rational powers. We haven't proved yet how to deal with differentiating x to a rational power. Once we have the chain rule, we'll have the ability to do that, though. Let's do another one. Okay, this relates to the product rule, generalizing the product rule apparently. The regular old derivative product rule tells you how to differentiate a product of 2 differentiable functions. Well, what if you have more than 2 differentiable functions? I only know how to differentiate functions and products 2 at a time. So that'll be a constraint on how we establish the following. Part A says, suppose u1, u2, and u3 are all differentiable. Find the derivative of the product of those 3 functions. Part B says, suppose u1, u2, u3, and u4 are differentiable. Find the derivative of the product of those 4 functions. And we're looking for a pattern. And my square bracket notation will definitely reveal a pattern on the generalized product rule. All right, first, let's take a derivative of the product of three functions. But all I know how to do with the derivative product rule is differentiate two functions at a time. Okay, let's group these first two together, get these parentheses to associate the first two together, and we'll treat u1 times u2 as the first function and u3 as the second function. You want to group them differently, go right ahead. But I choose to group the first two together, and now I've got a product of the first function, u1 times u2, times the second function, u3. Well, that's a product of two functions. We'll use a product rule. We'll take the derivative of the first function times the second function plus the first function times the derivative of the second. The only thing a little oddball is the first function is itself a product of functions. Okay. Here's where we left off on the previous page. So to differentiate this product, we'll have to use a product rule. We already used a product rule once, we've got to use it a second time because we got another product of two functions. How do you differentiate these two functions? Derivative of the first times the second plus the first times the derivative of the second. Still have that u sub 3 of x outside, and we still have this term stuck on over on the right-hand side. Okay, so we haven't actually differentiated anything yet. I mean, I don't know what these functions are, so all I'll do is say u1 prime for the derivative, and let's put square brackets around things that are derivatives, as we're prone to do. So derivative of u1 is u1 prime of x. Here's the u2 of x, u1 of x. Derivative of u2 is u prime of x. Remember that quantity there, that sum of those two things is multiplied by u3 of x. So there's a u3 of x. Here we've got u1 times u2 times what? u3 prime of x. u3 prime of x in square brackets. Let's distribute the u3 onto these two terms, and then we have u1 prime times u2 times u3 times that product of 2, now u3 times this product of 2, u1, u2 prime times u3, and over here we've got u1 prime, u2, u3 prime. And there's a very suggestive pattern there. We just differentiated three functions, u1, u2, and u3. Hey, and this is u1 times u2 times u3 plus u1 times u2 times u3 plus u1 times u2 times u3, but the first one's differentiated in this first trio, the second one's differentiated in the second trio, and the third one's differentiated in the third trio. Let's go to the next slide and rewrite this. Let's get rid of all the x stuff. I mean, that's a dummy variable, really. And let's just write it as the derivative of u1, u2, u3 is the derivative of the first times the second two, first times derivative of the second times the third, first times the second times the derivative of the third. And you see a little pattern, and that little pattern is consistent with the product rule for two functions. What do you think is going to happen when we differentiate 4? Okay, we'll go through and use a product rule. We'll do the manipulations quite similar to what we just did, and you'll see that this pattern holds. We'll have products of 4. There'll be a fourth one written over here. We'll differentiate the first, the second, the third, and the fourth in each of those products, respectively. So differentiate u1 times u2 times u3 times u4. Let's associate this as a product of two functions. The first function, let's associate the first three. I already know how to differentiate a product of three functions. That was part A. So we'll have this function, u1, u2, u3, times the second function, u4. So we'll have the derivative of the first, u1, u2, u3, I'm counting as the first, because I can only do 2 at a time, times the second, u4, plus the first, u1, u2, u3, times the derivative of the second, times the derivative of u4. Regular old product rule, theorem 3.3.g. Do you know how to differentiate a product of three things? I do now. That was part A. So how convenient. So differentiate this product of three things. Okay, that would be something like this. I'll keep the x's in it. That's a notation we're using here for now. We'll clean it up here shortly. So we'll have the derivative of the first times the second and the third, first times the derivative of the second times the third, plus the first times the second times the derivative of the third. And that's this derivative of the product that sum of three terms is then multiplied by u4 of x. So there's a u4 of x. It's multiplied by this stuff here, got square brackets, isolating those terms there because they're a derivative. Plus u1, u2, u3 times the derivative of u4 will denote as u4 prime and put it in square brackets. So all we need to do is distribute. We'll take the u3, distribute it onto this term, and that term. And we'll have four terms added together then. And we get the following. Okay, upon distributing, yeah, we get four terms, each involving a product of four things. In the first term, we've differentiated the first thing. In the second term, the second thing. In the third term, the third thing. In the fourth term, the fourth thing. Looks like I'm missing a prime on that. Get it down here, yeah. That's a little typo, I need a prime right there. But that's the pattern we have. If I forget all those x things, then we get the derivative of the product of four things is derivative of the first, second, third, and fourth. First, derivative of the second, third, and fourth. First and second, derivative of the third and the fourth. First, second, third, derivative of the fourth. A pretty clear pattern on how you differentiate a product of several functions. Let's return to the notes and get some more mileage out of my square brackets. Okay, so in this previous exercise, we saw the derivative of a product of three things behaves like this. The derivative of a product of four things behaves like that. Well, what if you differentiated n things, an arbitrary number of a product of functions? So the pattern's pretty clear. The square brackets reveal it quite explicitly. We could use mathematical induction. That's described in Appendix A2, a bit of a non-standard Calculus 1 topic, even though it's in the book. And we could see that if we differentiated a product of n functions instead of 2, 3, or 4, say u1 times u2 times u3, dot, 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 up through u sub n. So if we had a product of n subscripted functions multiplied together, and we differentiated it, what do you think can happen? Well, in terms of the parentheses and square bracket notation, we'd have something like this. You differentiate that product of n things, you're going to write those n things down n times. So I've got n parenthetic terms here, dot, dot, dot. I don't know what n is exactly. And I'll simply write those things down a total of n times. But in the first expression, we'll differentiate the first term. In the second expression, we'll differentiate the second term. In the third expression, we'll differentiate the third term, and so forth. Some dots here because I don't know how many I've got there. We'll differentiate the second to the last. We'll differentiate the last, and of course, all those intermediate ones. And what you see when I lay it out in an array like this, you see those square brackets working their way along the diagonal of this little array. So there's how you differentiate a product of n things, and there's how you would illustrate it using my square bracket notation. One more time, I made the square bracket stuff up. It doesn't mean anything to the rest of the world, but it does make the bookkeeping on these kinds of things pretty streamlined. Okay, something that will be surprisingly useful in our future is the idea of higher order derivatives, mostly second derivatives, but higher order derivatives are out there and play a big role in calculus too. But for us, first derivative and second derivative are primarily what we're concerned with. And these are defined as follows. If f is a differentiable function, say with derivative f prime, then we could maybe take the derivative of f prime, the derivative of the derivative, call the second derivative and denote it f double prime. The second derivative of f. If we let y equal f of x, then we have the following notations. The second derivative could be denoted as the derivative with respect to x of the derivative of y with respect to x. We might denote it as y double prime. In the differential notation, remember this d dx thing means take the derivative. So this would be read, take the derivative of the derivative of y with respect to x. Or if you like, and you want to isolate the derivative stuff here, I can do it, the d dx stuff here, we'd have take the derivative with respect to x of the derivative with respect to x of y. Differentiate it twice. I go through this weird explanation because the standard notation is to write it like this. So this indicates a second derivative. Notice they look like exponents. Don't think of them as exponents. They're not powers. They're repetitions. Repetition of the process of taking a derivative. Though I might even read it d squared, dx squared. But it's the second derivative with respect to x of this thing sitting here. So it's a second derivative with respect to x of y. And it's common to put a little 2 up there and a little 2 down here. You don't put the 2 outside, or don't put it on the y or something like that. You've done this thing twice. You've ddx'd twice, and that's the reason the 2's go where they put them. It's just notation. Maybe it ain't even that great a notation, but it's a standard notation. And we could take higher order derivatives. We could take third derivatives or fourth derivatives. Instead of y double prime, we could take y triple prime. That'd be the derivative of the second derivative. The fourth derivative would be the derivative of the third derivative. The nth derivative would be the derivative of the n minus first derivative. It might take me a while to compute that. With all this product rule, quotient rule stuff, taking higher order derivatives potentially could be monstrous, because it seems when we differentiate, the derivatives get bigger. Sometimes they do, sometimes they don't. Many of the examples we've seen, the derivative was bigger than the original function. So if you took higher order derivatives, you got more and more product rules and more quotient rules and maybe more and more other stuff, potentially. One final comment on the notation. After about the second derivative, it's common not to write out a string of a whole bunch of primes, but to use a little 3 in parentheses. Make sure you put it in parentheses when you're indicating higher order derivatives. That parentheses sometimes can appear on the f as well. F in parentheses 3 of x would be the third derivative. But the little parentheses indicate that you're dealing with derivatives. Again, maybe not a great notation, but a pretty standard notation. You'll see this again. We'll use it again for one thing. So higher order derivatives, there's a notation for them. I look for physical meaning for these. First derivative will have a very physical meaning and a very useful application when we graph functions. Second derivative will have a very physical meaning in certain settings and be very useful when we graph things. Third derivative will have a physical meaning and we probably won't use third derivatives to graph things. They reflect a certain very subtle property of the graph. Really, when we graph things, we'll use derivatives big time. It'll be one of the main applications of derivatives, but it's mostly the first and second derivatives we'll use. I don't think when we're graphing we'll really ever look at a third derivative. Now let's do 3 more examples and then we'll finish up this section. Okay. Here's your function, y equals x to the 5th over 120. Not a very complicated one. They say find all derivatives. Find the derivatives of all orders of this function. Okay, it's really just a constant multiple of a power of x, so easy enough. First derivative, we'll differentiate y, x to the 5th over 120. That is 1 over 120 divided by 120. Bring the exponent down, subtract 1. Positive integer exponent, good to go. You want to simplify it. I haven't been big on simplifying. Let's simplify it because I'm going to have to do something to it. So if I don't simplify now, I run the risk of having really complicated stuff down the road. I won't simplify unless I'm worried about things becoming complicated later, or if I have to use the derivative for something. So let's simplify. Let's take the 5 divided by 120. It's what, 1 over 24. 24 times 5 is that's 120. So cancel the 5 and the 120 to yield a 24 in the denominator. And we've actually got x to the 4th over 24. There's y prime. Differentiate that. Okay. That's 1 over 24. I'll bring the 4 down, subtract 1 from the exponent. We'll get a 4x cubed. You want to simplify? No, but it would be the prudent thing to do. Take the 4, cancel it with a 24, because you can do that. It leaves you with a 6 in the denominator. X cubed over 6, that's the second derivative. Do it again for the third derivative. Differentiate x cubed over 6. Okay, that'll give us 1/6, 3x squared. I looked at 3 goes into the 6. That's why they chose this 120 denominator. The 3 goes into the 6, leaving us with x squared over 2. That's the third derivative. Differentiate that to get the fourth derivative. X squared has as its derivative 2x. Cancel the 2's, you get x. Differentiate it again to get the fifth derivative. Derivative of x is 1. Now what? Well, it's actually said find all orders of derivatives. Okay, differentiate it again. Derivative of 1 is 0. Sixth derivative is 0. Now what happens? Well, now when you differentiate 0, you get 0 out. So it's kind of stabilized. So from here on out, all the derivatives will be 0. They said find all orders. So that would be the first, second, third, fourth, fifth, and sixth derivative and higher. Those are all 0. So we did find all orders of derivatives like they wanted. Good thing it wasn't a bunch of exponential functions and quotients and stuff in there. This could have got out of hand quickly. So that's the reason they gave you such an elementary function, because they wanted you to calculate derivatives until things stabilized. A little application type thing concerning what we know. Says assume that functions f and g are differentiable and f of 2 equals 3, f prime of 2 equals -1, g of 2 equals -4, and g prime of 2 equals 1. Notice a pattern. They told you what these functions and what their derivatives do at 2. So they're probably going to ask us something about what happens at 2. They say find an equation of the line perpendicular to the graph of capital F of x equals lowercase f of x plus 3 divided by x minus g of x. I told you so. At x equals 2. Okay, equation of the line perpendicular to the graph of this function at x equals 2. All right, perpendicular to the graph. When we talked about that, that's a line that's perpendicular to the tangent line, and we find graphs, lines tangent to graphs at points using derivatives. So we'll find the slope of the tangent line using a derivative at 2. And then we'll take the appropriate manipulation, negative reciprocal, to find the line, the slope of the line perpendicular to that. All right, so first we need capital F prime. It's a quotient, so we use the quotient rule. Derivative of f prime, derivative of that quotient is, usual thing, it's the derivative of the numerator. Okay, let's actually do the differentiation, so we're not here all day. Derivative of the numerator is what? F prime of x plus 0. Well, whatever f prime is. They didn't tell me what f is specifically, so I can't tell them what f prime is specifically, but we can do it symbolically. Derivative of the numerator times the denominator minus numerator times derivative of the denominator. Derivative of x is 1, derivative of g, it's g prime, divided by the denominator squared. So there's capital F prime. Can we simplify it? Not much, eh? We can get rid of the 0. That's about it. We can get rid of the square brackets. We're about to do some algebra. Oh, I might point out, yeah, there's a square brackets, round brackets, minus round brackets, square brackets over round brackets squared. So it's got my little picture of the quotient rule in there, just by the way. So here's the derivative. All right, so they talk about a line perpendicular to the graph at x equals 2. When we got the derivative, if we plug in x equals 2, that'll tell us the slope of a line tangent to the graph of this function at x equals 2. All right, well, that's a necessary intermediate step, so let's do that. F prime of 2, plug in 2, you get a f prime of 2, you get a g of 2, an f of 2, a g prime of 2, a g of 2. You know that stuff? Well, that's why they gave us all that information. Yeah, I know what happens at 2 for f and g and f prime and g prime. And that turns out that's exactly what we need to know. So substitute in these values for f, f prime, g, and g prime of 2. Substitute those numbers in. As usual, I put in parentheses the things that are substituted in. Do the arithmetic and simplify. I encourage you to double check this on your own time. It looks like we get -1/6. So what's that tell you? F prime of 2 is -1/6. Tells you the slope of a line tangent to a graph of y equals f of x is negative 1/6. Tangent line has slope negative 1/6 there at x equals 2. We don't want a tangent line. We want a perpendicular line. All right. Well, we'll take a negative reciprocal of this to find the slope of a line perpendicular to the graph of the function there at x equals 2. So f prime of 2 is negative 1/6. That's the slope of the tangent line. We want the slope of the line perpendicular, not the tangent line. Okay, we'll take a negative reciprocal of this. Negative reciprocal of negative 1/6 is positive 6. Negative 1 over 6 is positive 6. Take the negative reciprocal of this, gives you the 6. So this will be the slope of the desired line, as I call it, the line perpendicular to the graph. All right, so how are we doing? We got the slope of the desired line. They want an equation for it. We need a point. Oh, that's no problem. We got the function. All we got to do is plug 2 into the function, and that'll give us a point on the curve. We've got the slope. We need a point. Plug 2 into the function. That'll give you the x value, and out will pop the corresponding y value. F of 2, plug the 2 in, you know, lowercase f of 2, and you know g of 2. That was given information up here. Plug those values in. Simplify, you get 1. Again, I encourage you to double check the arithmetic. Pause the video and convince yourself. So we've got the point, x1, y1. That would be 2, capital F of 2. That would be x was 2, and the function value was 1. So it'd be the point 2, 1. So we're looking for a line with slope 6 passing through the point 2, 1. Well, you got the point slope formula of the form, say y minus y1 equals mx minus x1. I know m is 6, x1 is 2, y1 is 1 from the point on that line. Plug that information in. That produces y minus 1 equals 6, x minus 2. Rearrange, we get y equals 6x minus 11. I got the right slope. I got slope 6 like it's supposed to. Does it pass through the point 2, 1? When x is 2, we'd have 6 times 2 is 12 minus 11 leaves us with 1. Right, it passes through the correct point as well. So there's the line perpendicular to the graph of this function at x equals 2. Hey, what if they just ask you for the tangent line? Well, then we would have used the derivative. We'd have used negative 1/6 for the slope, and we'd use the same point. So we would have had a slope of negative 1/6 instead of a slope of 6, and the numbers would be modified accordingly. That we've done a lot of. We've done a fair amount of finding equations of lines tangent to curves. Here's a little something new, finding the equation of a line perpendicular to a curve. It just has this added little step of a negative reciprocal to convert the derivative into slope of a perpendicular line. Okay, this is number 80, 3.3, number 80, high numbered problem. It's actually not complicated at all. So let's read through all the verbiage. One of the formulas for inventory management says that the average weekly cost of ordering, paying for, and holding merchandise is A of Q equals Km divided by Q plus C times M plus HQ divided by 2. Q is the variable. Where Q is the quantity you order when things run low, shoes, TVs, brooms, or whatever the item might be. K is the cost of placing an order, the same, no matter how often you order. C is the cost of one item, a constant. M is the number of items sold each week, a constant. And H is the weekly holding cost per item, a constant that takes into account things such as space, utilities, insurance, and scrutiny. Find dA dQ, derivative of A with respect to Q, and the second derivative of A with respect to Q. All right, that's a long story. How hard is this? Not hard at all. Got a bunch of letters in it, but they've made up. I'm no business savvy chap myself, but they've made up a story to fit what you can do. Everything's constant, isn't it? Well, Q's not. Q's the quantity you order when things run low. It says A is a function of Q, so Q's a variable. But K is the same all the time. It's constant. And they told you the other things. They actually use the term constant. What is it? C is constant, M is constant, and H is constant. So C, M, H, and K, all those things are constants. Well, I know how to deal with derivatives when we've got constants. So the only thing that varies is Q. A of Q, we got a Q here, and we got a Q here. All the other stuff is constants. It's just numbers. Okay, they're represented in numbers with letters, but they're just some fixed number. So we're really taking the derivative of something divided by Q plus a constant times Q. Easy enough to do. And we'll take a second derivative from that. Okay, so we've got A of Q, it's given by this formula. Q is the variable, and all the other stuff is constants. Okay, let's take a derivative then. Derivative of A with respect to Q would be the derivative of this stuff here. That would be the derivative of the first, derivative of the second, ooh, that's constant, plus derivative of the third. Here, I say we got a quotient. You want to look at it a different way? Maybe you could. We will, but I'm going to treat this as a quotient because we've done a lot of stuff with a quotient rule lately. There are other ways to do it, but I say quotient. You want to do it a different way. As long as it's legitimate, I'm happy. And we'll do some a different way, but now we're still kind of enamored with a quotient rule. I got a quotient. Okay, so like it says, we'll need the derivative quotient rule. So we'll differentiate the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. There it is. Square brackets, derivative of the numerator, derivative of K times M. Km's a constant. Its derivative is 0. Times the denominator minus the numerator, Km, times the derivative of the denominator, derivative of Q with respect to Q, just like differentiating X, it's just 1. And then we get the Q squared in the denominator. Quotient rule, I can tell, because I see the square brackets. Here we're just differentiating a constant. C and M are constant, so C times M is a constant, and the derivative is 0. Here we've got H over 2 times Q. Well, the derivative of Q is just 1, like it was over here. And we just pick that constant up. So we get for the derivative of HQ over 2, or maybe better, H over 2 times Q, we just get the H over 2. That's a constant. That's the constant coefficient. Because they told us all those things were constants. So let's clean that up because it'll clean up a lot. And because we're going to have to take a second derivative. So we lose the 0 term here. This becomes what? Negative Km over Q squared. Negative Km over Q squared. That's gone. 0 plus H over 2. So there's what we get for the first derivative. How about we write this divided by Q squared as Q to the negative 2? I could treat this as a quotient like we previously did, or I could treat this as Q to the negative 2. I could have treated up here, I could have treated this 1 over Q as Q to the negative 1. If I did that, I wouldn't have needed the quotient rule. But like I said, I was enamored with the quotient rule. Well, I ain't that enamored with it. Let's treat this as Q to the negative 2. You want a quotient rule, let's go right ahead. You want to treat this as Q to the negative 1, go right ahead. So I'm just doing it both ways. All right, so we can rewrite this by bringing the Q to the numerator as a Q to the negative 2 and say, there's another version of the derivative. They want the second derivative. Okay, the second derivative of A with respect to Q would be the derivative of this thing, the derivative of the first derivative. Okay, you need to differentiate this multiple of Q to the negative 2. Well, there's the multiple. Bring the negative 2 down. Subtract 1 from negative 2. Negative 2 minus 1 is negative 3. Be careful when you have negative exponents and differentiate. We've done this before. You subtract 1 from negative 2 and you get negative 3. It really did reduce by 1. You're used to seeing 2 go down to 1 or 3 go down to 2. And it went down. This looks a little different because these are negative numbers. -2 went down by 1 to -3. It's a consistent story. And then the h over 2 is a constant, so the derivative is 0. And we're left with, I can cancel the 2 negatives if you like. We're left with 2km q to the -3. Could you take a third derivative? Actually, yeah, it wouldn't be too bad. We just bring the -3 down, subtract 1, get a -4. Could you differentiate that? Yeah, we'd keep bringing exponents down and subtracting 1. That one we did with the x to the 5th over 120, we differentiated it until we got to 0. You differentiate this all you want, it ain't going to go to 0. There's a pattern, but it won't go to 0. So this one's somewhat more complicated if we were asked to find higher and higher order derivatives. They wanted a first and second order derivative. Told you, it's not that tricky. They just muddled up the problem with all these K's and M's and C's and H's. They were all constants. It was actually a fairly simple function in Q. It's good for you to practice these kinds so you don't get too enamored with what the variables are and what the constants are. All these letters, just treat them as if they were numbers, because they are. I just don't know what number they are. There's some constants. And yeah, that takes care of that section. So goes section 3.3. So we'll move on to 3.4 next. I think it's a little bit shorter than this one. You're getting good at differentiation. There's a little bit more to learn, but you're getting quite good at differentiation. I'll see you in section 3.4 shortly. Have a nice day.